Yep. Right. Hi,
Okay,
everyone. Welcome to today's stream. Welcome to today's stream, everyone. We are so happy to have you today. Um, I'm trying to see who is on the stream. If you're on the stream, can you kindly drop a comment so we can see you? Drop a comment in the chat. Kingsley, someone beat you today to someone came before you today, and that is Obasoro. Obasoro came before you today. Thank you very much, Obasoro. Thank you very much for coming. Kingsley, we are happy to have you today. You're welcome. Welcome to today's session. So if you are here with us, can you drop a comment? Drop a comment. Drop a comment on the chat box. Hi, Pamela. Pamela, you're welcome. Kingsley. Kingsley, we see you. All right, guys. So you guys know how we do it. In the next 1 to 2 minutes, let's share let's share this on our YouTube, on our WhatsApp status. Share this to everyone. Anyone you think that would be interested, go on the WhatsApp group, drop a message on the WhatsApp group, tell them that we've started. Just go on the WhatsApp group and drop a message. Disturb everybody, tell them that we've started. They should join the live. We just have about 5 people here watching just on YouTube. I don't know how many people are watching on LinkedIn, but then yeah. So guys, make sure to I'm waiting for more people to join the live before we get started. Francis is here. He's ready to get start going. You guys should bring other people. Go and wake them up on WhatsApp. All right, I can see we have more people on the live. All right, so this is week. Week what is this, guys? Let me see in the comment section. Week what are we in? What week is this? This is another way for me to know those that are doing their tests. They're doing their task. What week is this, guys? This week what? Maybe I should give a gift for this. What week are we in? Nobody's saying anything in the chat. So you guys don't know what week we are in. Okay. All right. So this is week 6, right? This is week 6. And then we have about so we are gradually getting to the end of this whole thing, and I hope that you all are learning from it. All right. So I think we have enough people on the space, and then we'll spend more time. So without spending much time, um, I'll be the next voice you'll be hearing will be that of Francis. Francis is a ZK proof expert. ZK means zero knowledge proof expert, and then he will be the one taking us on today's session. Right. So everybody, please pay attention. You guys know how we do it. Answer any question that he has, follow through, and then most importantly, invite your friends to join the live. Thank you. Hi, Francis. Can you hear me?
okay, yes, I can hear you.
Okay, okay, okay. So you can go on and yeah, I think
Okay,
your screen is up already.
yeah, yes. Hello, everyone. Can you see my screen? Just indicate in the chat section if you can see my screen and if you can hear me well. Hello. Seems nobody can hear me. Okay. Thank you, Kwasu. Thank you, Kingsley. Thank you, Akim. Okay, without wasting much time, we'll be jumping into the session for today. And please, if during the course of the session, if you have any questions, please feel free to ask. Yeah. So just feel free to unmute and ask. Um, okay. Yeah. Yeah. I'll also be checking the chats, but feel free to unmute and ask. Okay, so today we'll be talking about zero knowledge, right? How many of us have heard about zero knowledge before now? And I would like the class to be as interactive as possible. So, I would like to know how many of us have heard about zero knowledge and what did we hear about it? Like, if someone was to ask you what is zero knowledge, like for those that have heard about zero knowledge, right? If someone was to ask you what is zero knowledge, what would be your answer? Does anybody want to try? Okay. Um, Seems nobody wants to try, right? Okay, so let me just shoot for it then. Okay, so zero knowledge is a subfield of maths and cryptography that enables someone called a prover to prove to another person called a verifier that a statement is correct without revealing anything about any other information. Like this kind of like the textbook definition, right? Where you have like one party, you have two people. One party is called a prover and another party is called a verifier. And the prover is trying to prove to the verifier that a certain statement is correct without um, revealing any other information about the statement. Like a lot of people, when they hear zero knowledge and they hear the definition, it often sounds like magic, but then it's not magic, right? Like everything is backed by mathematics. So it's basically mathematics under the hood doing what you think is magic. So a colleague of mine would like to, like when talking about zero knowledge, she would like to say or use this illustration where you have two people where you have two people and then you have a very small man and then one person wants to prove to the other person that he did something correctly, but he doesn't want to show, like, okay, we're going to use like a prover and a verifier just to differentiate these two people. So the prover wants to prove to the verifier that he did something correctly. And then there's this very small man that the verifier has. And what the verifier does is that the verifier, both the prover and the verifier trust the small man. So the verifier gives the prover the small man and tells the small man, okay, watch this guy, like watch everything he does and make sure that he does everything correctly. And then the prover takes the small man, goes and do what the verifier told him to do. And after doing it, he comes back to the verifier and gives the verifier the small man. So both the prover and the verifier trust the small man, right? So and they trust the small man not to reveal anything that he has learned along the way while watching the prover to the verifier. So When the verifier receives the small man back, he just asks him, is what the prover said true or false? And the small man tells him, like, yes, he did it correctly. And that's basically the only thing the verifier learns about the entire statement. So here we're talking about a small man, but in practice, that small man is actually mathematics. So mathematics is this um, field, or is this thing that everybody can trust, right? You can always trust that 1 plus 1 is equal to 2 anytime, any day, right? You can. So in the case of ZK, mathematics is what we actually like move that need for trust between the provider and the trusting mathematics to be honest. And just as we know, like mathematics is technically always honest. Um, I hello, please can everyone hear me?
Yeah, you were cracking at some point, Francis, but I think we can hear you now.
Okay,
Can you hear me?
yes, I can hear you very
Yeah,
well.
you were cracking at some point, but we can hear you.
I can hear you very well now. So, at what point did you stop hearing me? Sorry.
It's not like we stopped, but it was breaking and coming back.
Okay, it was just breaking. Okay. Okay. So, um, like,
Yeah.
does anybody have any question about like what I've said so far about the prover and the verifier? Yeah, and the prover proving to the verifier that a statement is correct without revealing any other information, and then both parties trusting mathematics because math almost is always honest, right? Okay. Does anybody have any question? Math is technically honest. Yeah. Okay. So please, if you have any question, just feel free to um I don't know if you can unmute and ask, or if it has to be in the chat. But please feel free to ask.
Actually on YouTube, so just go on. You can ask questions at the end.
Okay. Okay. So okay, so up next, so we're talking about like the properties of zero knowledge, the properties of ZK. So there are three major properties. We have completeness, soundness, and zero knowledge. So when we talk about completeness, what we basically mean is that if a prover is honest, that means if the person trying to convince the verifier that he did something correctly, if he actually did that thing correctly, then he should be able to generate what we call a proof that the verifier will always accept. So, in as much as the prover is honest, then the prover will always generate a proof that the verifier would accept. So that is what completeness means. And then when we talk about soundness, we're talking about like if the um when we talk about soundness, we're technically saying that if the verifier accepts, that means the proof was valid. Like these are two different things. Completeness, if the prover is honest, then the verifier will always accept. And then for soundness, if the verifier accepts, that means the proof was valid. So they can, in a situation where the verifier accepts, but then the prover was not honest, that would be like breaking the soundness property, right? Because the prover lied, but then the verifier still accepted what the prover said to be true. So that is breaking the soundness property of zero knowledge. And for the completeness property, if the prover was honest, like the prover did what he was meant to do, and then the verifier did not accept, that will be a break in the completeness property of zero knowledge. So these are like two, they sound pretty much alike, but they are two different things. The completeness property and the soundness property. And then we have the zero knowledge property. And what the zero knowledge property just says basically is that if, like, after the interaction between the prover and the verifier learns nothing new. Like, okay, let's use an example. For example, a prover is trying to prove to a verifier that his age is, let's say, 30, right? And then they have this interaction. The prover, the verifier asks questions, the prover answers those questions. And then after the interaction, the verifier accepts. So if we take the verifier before the interaction and after the interaction, the only thing that the verifier should know is that the prover is above the age of 30. Like if the verifier knows any other information, then the zero knowledge property was broken. Right? So even if the verifier, like during the course of the interaction, learns the age of the prover, then the zero knowledge property has been broken. Like the only thing the verifier should know after the course of the interaction is if the statement was true or false. No extra information leak. Okay. Um, so next we'll be talking about like the uses of zero knowledge. So a lot of times when we hear zero knowledge, zero knowledge, zero knowledge, like especially in application, most times it's not actually zero knowledge. Like, there are different uses of zero knowledge, and we're going to talk about it. We have privacy, which is similar to the case of proving your age, right? Or proving that you're older than 18. So in the case of privacy, you're hiding some information and then you're proving that um, you're proving that a statement was correct without revealing any information, right? So that's technically the case for privacy. And then like zero knowledge can also be used for computation delegation. But when I say computation delegation, I mean like say we have two parties, um, me and let's say you, and you want to perform a, like you have a program you want to run on your computer, but then your computer cannot run that program, maybe because you don't have enough RAM or space. But then say I have a supercomputer that can actually do that computation. So instead of you to do that computation, since you don't have the resources, you can delegate that computation to me since I have the resources to do the computation. But then How can you trust that after I have done the computation, the answer I gave you was correct? Like, because you could give me that program to run, and since I know you cannot run the program, right, I could as well just lie to you and tell you that the final answer when I ran your program was 500 when I did not run the program at all, right? So, in the case of computation delegation, it enables someone with low computational capacity to delegate computation to another party with a higher computational capacity, but still be able to verify that the party with the higher computational capacity actually ran the program and the party like is not just lying, right? So, and in order to do this, basically maths comes in, right? So maths is basically like the small guy we talked about. And then in this situation, when we send the program to the other party with the higher computational capacity, we also send him the small man, right, which is maths. And after he has executed the program, he sends the results back together with the small man, and then the verifier can accept. So, like, these are the major uses of zero knowledge at the moment. There are still other uses that are still like being explored, but at the moment, these are kind of like the two um, major use cases of zero knowledge: privacy and computation delegation. Okay, so when we talk of computation delegation, one thing that comes to mind is the roll up L1, L2, and roll up architectures, right? So there is the optimistic roll up and there is the ZK roll up. And what these roll ups do is basically, uh, or what these roll ups help the L1 do is basically computation delegation, right? Let's use an L1 like Ethereum, for example. We know how long it takes a block to be finalized on Ethereum, but then we want to be able to do more computation. So what L2s do is basically take some of those computation, perform the computations, and then send a summary of those computation to the L1. And there are basically like two roll-up architectures, which are like the optimistic and the ZK roll-up architectures. For the optimistic rollup, any transaction that the optimistic rollup executes, after executing, the optimistic rollup just summarizes all those transactions. Like they execute a lot of transactions, right? And then they summarize it and send it to Ethereum, which is the L1. In this case, the L1 is the verifier and the the roll-up says a prover. But in the optimistic case, there is no notion of proving and verifying. What the L1 just does is it executes, or what the optimistic rollup just does, it executes all the transactions, summarizes them, and sends them to the L1. And then there is this period of waiting where if anybody finds out that there was an issue in the execution of any of the transactions that was summarized, then the person can raise a the person can raise a flag, right? And basically inform everybody that, oh, some of these transactions were not executed correctly. So in that case, like in the optimistic case, like the name implies optimistic, the optimistic rollup just executes those transactions and sends it to the L1, and it's optimistic, or everybody is optimistic that the transactions were executed correctly. If nobody tries to verify that those transactions were executed correctly, then it's possible for somebody to actually lie while executing those transactions. So the person does something malicious, and then, like, since everybody is optimistic that all the transactions were executed correctly, everybody just takes that as the truth. But in the case of the ZK rollup, after these transactions are executed, the ZK rollup will need to prove that those transactions were executed correctly to the L1. So the ZK rollup does not just summarize the transactions, it summarizes the transactions and also generates a mathematical proof that those transactions were actually executed correctly. So in the case of the ZK rollups, there is no need for those long wait times. For the optimistic rollups, I think the wait time is about 1 week, which is 7 days before a block is finalized, right? But in the case of ZK rollups, since a mathematical proof has been generated already, all what the L1 needs to do is just verify that the proof is correct. And once the L1 verifies that the proof is correct, the L1 accepts all the transactions that were summarized by the ZK rollup. So with this, we can see that there is kind of like a reduction in the time it takes to achieve finality of the transactions or the summary of those transactions. The L1 accepts the summary way faster than it accepts the optimistic um, roll up summary. Right. Does anybody have any questions so far? Okay. So these are like some examples of ZK rollups, right? There are a lot of ZK rollups, but these are just a few of them. We have Stacknet, we have Scroll, we have Polygon Midin, we have Aztec, we have ZK-Sync. There are quite a lot of them. And these different rollups use different proof systems to actually prove that all the transactions that were executed on them were executed correctly. It uses a proof system called the stack proof system, right? So they use that to prove to the L1 that all the transactions that were executed on them on Stacknet was executed correctly. So for scroll uses a snark, a zk-SNARK, and basically just to do the same thing, just to prove that all the transactions that were executed on scroll were executed correctly. So we have the stack and snark, right? So the both of them are just different ways to generate proofs that can be verified by the L1, or let's say any other party that wants to verify. So these are like two different methods but the end goal is the same thing, like generating proofs that proves that the transactions that were executed on the rollup were executed correctly. So same thing. We also have like Polygon there, we have Aztec, we have zk, but basically each one of them just uses a flavor of the zk-SNARK or the zk-stack. So those are kind of like the two major stacks when it comes to generating zero knowledge proofs. So also there's the concept of prover and verifier networks. Generating these proofs are not so easy, right? Because in order to generate a proof, one, you need to execute, let's say, in the context of rollups, right? In order to generate a proof, you need to execute all the transactions that the the rollup wants to summarize, right? It needs to execute all those transactions and then summarize it. So the prover, basically, which are these rollups, are actually doing a lot of work because they will need to execute all those transactions and they will also need to generate a proof that those transactions were executed correctly. So generating this proof is kind of like extra work that the prover does so that the verifier does not need to execute all those transactions again. So the prover executes the transactions and does extra work, which is like generating proofs, while the verifier, which should have executed those transactions, don't need to execute those transactions again, right? Because the prover has done some extra work to generate proofs. So what the verifier just does is it takes the proofs that were generated by the prover and then it verifies the proof and either accepts or rejects what the prover says. So since this is a lot of work, like it requires a lot more computational resource than actually executing those transactions. And in the case of ZK-Rollups, they need to generate proofs of all the transactions that were executed on them. And the way a lot of them do it is by having prover and verifier networks where they can delegate the work of generating those proofs to a lot of computers, right? So instead of just one computer doing the work of execution of provers called the prover networks, right? And what these prover networks do is they generate the proofs for the L2, and they kind of do it in a better way, faster way, because like these are people that have a lot of computational resources that can be used to do the work. Right? So these are just some prover networks. We have the Lagrange prover network, we have Scroll prover network, Succinct prover network. And all these prover networks, what they just do is they generate proofs of execution. Right? And then there is a verifier network. So normally after the prover generate the proof, the prover sends the proof to the verifier. In the case of in the case of rollups, the verifier is the L1, right? But then, like Verifying these proofs is not so easy with the current state of um, verification. So they also have what they call verifier networks, where those proofs can be sent to be verified. And then if the proofs are valid, after the verifier network has verified, the verifier network sends um, a message to the L1 that, oh, this proof was valid, right? So there's technically no need to execute or to verify the proofs directly on the L1, because proof verification on the L1 is expensive because it requires like a lot of gas, and because it's computationally intensive, it's costly. Right? So verifier networks just help to offset that cost by doing the verification outside the blockchain, and then when the verification, like if the proof is valid, then the message is sent to the L1. So the L1 does not need to like do those heavy computational uh, work of actually verifying the proofs. Okay, so I'll also be talking about like domain specific languages. So just like we've seen, we have um, rollups, right? And like sometimes we may want to write our own programs, right? And let's say we want to write a program and we want someone to be able to prove to another person that something was correct in our program, not necessarily like on a blockchain scale. Right? So there are different languages that can enable us to write provable programs, and these are some of them. We have like Secom, we have Cairo, Noah, Leo. There are a whole lot of them, but these are just a few. So when writing your circuit, because that's what those programs are called. Let's say you have a program, you need to generate a circuit for that program. A circuit, you can think of a circuit as your normal um, electric circuits where current are passing through, right? Where we have different gates, we have OR gates and gates, and depending on the current that comes in, it determines what the output is. But in the ZK space, we tend to work more with arithmetic circuits, not Boolean circuits. So we're passing in numbers to a circuit, and we're passing in numbers basically to an arithmetic circuit, and that circuit is made up of gates, right? So when we talk about an arithmetic circuit, the gates in an arithmetic circuit can be either an addition gate or multiplication gate because we are performing arithmetic circuit. Right. In the case of a Boolean circuit, we'll have like maybe an AND gate, OR gate, XOR gate, or any other gate. But in the case of ZK, we work with arithmetic circuits a lot, and basically the gates you tend to encounter like addition gates, which takes two inputs, adds them together, and gives you an output, or a multiplication gate, which takes two inputs, multiplies them, and gives an output. There are also cases of like custom gates, but those are kind of like high level stuff. So when say you want to write a program to actually do some proving or verification, you can use any of these languages. So in second, you write your circuit, which is kind of like almost equivalent to designing like a Boolean circuit. Like the way second is almost equivalent to designing like a Boolean circuit, right? With your like for those that um, are electronic students, we know how it is like designing Boolean circuit. So second is something quite similar to that. You can write your program and as a circuit, and then you're able to prove and verify that program using existing libraries. So languages like Cairo, Noah, and Leo are more user friendly. So they tend to enable you write your program, whatever program it is. You can write it in a more friendly language. Like Cairo, Noah, and Leo are actually designed to be similar, very similar to Rust. Like they basically have the same syntax with the Rust programming language. So they can enable you to write your program just like you write, let's say, your Python code or your JavaScript code or your Rust code. And then under the hood, when you execute that program, they actually use mathematics to generate a proof for you that that program was executed correctly. And then with that proof, you can verify it. So Cairo is Cairo was built by the Starknet team, and like if you basically want to write a smart contract on Starknet, you'll be using the Cairo language, and it was designed to be provable. It's a provable language. Noah is um, was built by the Aztec team, and it's still like very much Rust-like, just like Cairo, and it enables you to write your program just like you would, and then you're able to generate a proof and also verify it. So like these languages and Leo as well, still Rust-like syntax. So with these languages, you can basically just write your program like you would any programming language, and it can generate a valid proof. You can generate a proof and verify that that program was actually executed correctly. Okay, so there are also other libraries, like these ones are just like some libraries that do a whole lot of math stuff. So for somebody who just wants to write a normal programming language, you can stick with the domain specific languages. But even these domain specific languages under the hood would need to convert the program you've written into a mathematical representation that can then be used to generate proofs, which can then be verified. Right. So these libraries, we have Aquox, we have Halo 2, we have Plunky 2 and Plunky 3. These are like libraries that do the heavy lifting. They do a whole lot of the math stuff under the hood so that you don't need to think about it. Right? So most of these high level languages also have libraries that they use under the hood in order to convert those high level Rust like programs that you've written to mathematics. So these libraries work under the hood to convert those high level languages to mathematics and then enables you like generate proofs and verify those proofs. Okay. So we're talking about the applications of ZK, right? So I'm sure like a whole lot of us have heard a lot about like ZK, but we're like, what is the use case, right? How can it be used, especially in real life, like in day-to-day activities? So these are like some applications of ZK. We have semaphore, which is a a tool to enable. It's kind of like a tool to enable private chats. I'm sure a lot of us know about this stuff. I forgot the name, but where you can send anonymous messages. Yes. So with Semaphore, you can send anonymous messages. Where you can create a group where anybody can drop a message, and then nobody knows exactly who dropped that message. So Semaphore is a tool that uses ZK to enable anonymous messaging. So you can have like anonymous group chats where, let's say, in a company, everybody in that company is in the group chat, and then somebody drops a message, but then nobody knows who exactly was the person that dropped the message. So that's basically what like semaphore is. And cursive is a way to like cursive is a company that builds toolings to enable you prove that you've actually met somebody in like real life, right? So they have this proof of personhood, they have this ring and this NFC card where when you meet somebody, you can tap the card in order to generate a proof that you've actually met this person. So if the two of you meet at another occasion, you can tell the person, "Oh, I met you so and so place." Even if the person have forgotten, you can just show the person the proof, the mathematical proof that, "Oh, this is a proof that I've actually met you, or I actually met you at so and so place." So that's what like this cursive does. We also have like privacy pools, which is another use of ZKP, where I know about Tornado Cash. Um, and there are other like privacy pool um, tools that are also being built. So it enables you send money from one person to another, but then hiding um, ownership basically. So you can deposit money into a pool of funds and then withdraw that money to another address. So you're using one address to send in the money and you're withdrawing with another address. So nobody can actually know that it is you that removed the money, or like they can't be able to trace you to know where exactly that money went to, or if it's actually you that withdrew the money, because you're withdrawing to another address. So it kind of like helps to create privacy for transactions. And then we have like ZK email. So ZK email basically enables you prove that you actually um, received a mail. So when you receive a mail, you can generate a proof that that mail was sent to you. Like this ZK email has had a lot of applications, like in ZK P2P, which enables like peer-to-peer trading um, by leveraging zero knowledge. So you can send money to a party and you generate a proof that you actually sent money to that party. And then with that proof, you can claim some tokens. Right. Like there are basically a lot of use cases for ZK email. And also we have ZK-TLS, which enables you to prove that a, a session, like an interaction with a server, basically it was like enable you to prove that you interacted with the server honestly. Like ZKTLS has also like it's kind of like still emerging, but there have been a lot of developments in the space and like applications that have been that are currently like trying to build on it. So like these are just some of the applications of ZK, and like there are still a whole lot of other areas like where ZK is being applied and is making things that were before not possible, making them now possible on chain. Okay, so I think that's technically just like a summary. I know like I've been talking a lot so far, and I guess some people, like some of you, may have some questions, and I think this will be a good time to ask them. Okay, so I can see a question. How do zero knowledge proofs ensure data privacy without compromising on verification? So under the hood, basically, like zero knowledge proofs use mathematics to hide certain information and reveal certain information. Right. So you can decide the information you want to hide and the information you want to make public. So they usually call them the public input and the private input. So like everything is basically done with mathematics. Like even after writing your high level language, like let's say Cairo or Noah or Leo, these languages are compiled down to mathematics. And with mathematics, you can prove a statement was correct. It's just basically like saying 2 plus 3 is equal to 5, right? And let's say, okay, in this case, it will be pretty easy because if, let's say, 2 was public, then it's easy for you to get 3, right? Because for you to get 3, you can just do 5 minus 2 to get 3. Let's say if 3 was private information, right? But when we start talking of things like elliptic curves, which can be used to like especially protocols that are built on the discrete log, um, hardness of the discrete log, elliptic curve discrete log problem, right? It's not so easy to just let's say move something over the equality sign and do subtractions in order to get like or reveal information. So, but technically, like, it's basically just maths under the hood, enabling you prove and verify that certain statements were actually um, executed correctly or not.
Thank you very much,
Okay.
Franz.
So
Yeah. I don't think.
yeah.
So, guys, any other question? Okay, I think there is one from Kingsley.
Okay. Okay. So what if in a scenario where a transaction fails, how can we investigate or audit, knowing fully well that ZK doesn't permit that? Okay, so in a language like Cairo, if the transaction fails, a proof is also generated to prove that that transaction actually failed, right? So that's why, like Cairo, when compiling a Cairo contract, they compile down to Sierra, which is an intermediate representation, which is safe. And then from Sierra, they compile down to the Cairo assembly, which is actually what executes on the Cairo virtual machine, right? So in that case, a proof is also generated that a particular transaction failed. And also, like that is also another thing, right? Especially when deploying ZK systems in the wild, they also need to be careful about that because if your ZK system has a bug, you you will not know. You will basically not even know that your ZK system has a bug. And if that ZK system controls lots of funds and somebody finds a bug in that your system, that means technically the person can withdraw all the money in your, let's say, your smart contract, and you will not even know, right? Because the verifier accepted, and for the verifier to accept, that means the statement was true, even when the statement was false. So that type of bug is something you, when designing like a, a ZK system or a ZK circuit, when building your circuit, you need to be very careful that your circuit is bug free. Because if your circuit is actually buggy, then it will be very difficult to actually pinpoint where the bug is, and then you can basically lose all your money without even knowing it. Okay, so how do zero knowledge proofs balance the paradox of proving without revealing? Isn't proof usually about showing something? Yeah, proofs are about showing that um, something is valid, right? And like there is the notion of randomness, where randomness can be used to hide some information, right? So even when like proving, you use randomness to hide some information, so like it doesn't really reveal any information about what is being proven. Okay. um If the prover constructs a proof using a valid witness data, which are encoded, transformed, and evaluated, how does the verifier check proof satisfies? Okay, so it's technically like, at a high level, it's technically like the example I used where we have like 2 plus 3, right, equal to 5. But if 2 was, let's say, an algebraic equation, 3 was an algebraic equation, and we needed to solve an equation that gives us 2, and we also need to solve an equation that gives us 3. And then the final output, which is 5, is meant to be the sum of the output of the two different equations, right? In that situation, right, the prover does the work of solving those two different equations and then getting 2 and 3, right? And then he sends that to the verifier, and the verifier just adds 2 and 3 to get 5. That's kind of like just a high level um, overview. I hope that makes some sense. So, to become a blockchain engineer or developer, is it a must to know all the programming languages you mentioned? No, definitely not. Like, you can just focus on one. Like, even basically with Rust, like currently with Succinct, you can prove the execution of a Rust program. Like your normal Rust program you write, you can actually prove that it was executed correctly, right? So you don't need to know all those languages. You just need to pick one of them and be good at it. Just pick one and be good at it. Okay. Um, any other question?
Alright, I don't think there's any other one. I've looked through all in the chat. Thank you very much. Thank you so much for coming. Okay, I'm trying to know.
Okay, I think just one more. I think
And let's
so.
ask one last question.
What's
Yeah.
okay? So what's the biggest misconception people have about privacy on the blockchain, and how do ZK help correct that? Okay, so a lot of people tend to feel that at the moment that the blockchain is actually private. And I would say no, the blockchain is not private. Like it is pseudonymous, right? Which means you don't know exactly who is sending some funds, but then you can know. And once you know who one person is, it's easy to map out who, like people that have interacted with that person. So it's not completely private. The current state of the blockchain is not completely private. It's um, pseudonymous, not private. And even uh, with the advent of ZK rollups, right? Most times we hear ZK rollups, ZK rollups. Those rollups are not actually zero knowledge. What they actually do is just the what they actually do is in most cases, like for most of those rollups, is just computation delegation. So there is nothing about privacy. They just help Ethereum outsource computation. Yeah. Um,
Oh,
so blockchain is secure but not private, which is where ZKP come in. Okay. Yeah. So the blockchain is secure
thank
because it's
you.
decentralized, right? But then it's not private. But then it can be private with ZKPs, and a lot of people are currently working on making it private, especially when with protocols like privacy pools and like a whole lot of other protocols on development. Okay, so thank you for the questions
All right,
and
thank you so much. Thank you, thank you, thank you, thank
uh,
you, thank you. All right,
thank you
guys.
for
Yeah,
having me.
you're
Looking forward to more of
welcome.
this.
You're welcome. Yeah. So, guys, we'll be sharing the link for the task and also the tax. We'll be sharing the tax with you on the WhatsApp group. So, if you're not on WhatsApp, make sure you are there. We'll share the task. If you are not the one for last week, please make sure to submit, and then yeah, we'll be sharing the tax there. And I hope that you will submit the tax. Yeah. So, thank you. I'm trying to drop the link to the assignment for this week on the chat box. So if you hang around, you will get it in the chat. Write a summary on how ZK proof. Like I said, some people doing, are still not publishing their work. I mean, it's okay to be shy, but God doesn't care if you're shy. So I just sent the assignment in the chat. So guys, please make sure to do the assignments, and then we'll see in the WhatsApp community. Thank you very much, Francis. Thank you so much for explaining this. And thank you very much, everyone that attended. Enjoy the rest of your weekend. Yeah, bye bye. And happy Easter to you guys too. Happy Easter. Happy Easter, Francis.